Let's look at the rest of 2.3. So before we've taken derivative of sines and cosines. But they wait to 2.3 to do the derivative of the other four trig functions. Now why is that? Well, for example, if we want to take the derivative of tangent, we don't have that yet. But notice that tangent can be written as sine over cosine. If we want the derivative of, let's say, secant, secant is 1 over cosine. Now, this is not the derivative of secant, it's just secant is related to cosine this way. Cosecant is equivalent to 1 over sine. And cotangent, if tangent is sine over cosine, cotangent is cosine over sine. So if we know the derivative of sine and we know the derivative of cosine, notice all of these are quotients involving sines and cosines. So we could find all of these other derivatives. Now, we're not going to go through and show you the long way to get the derivative of all four of these. We will on the first one, but then the other three, I'll just give you their derivatives. So the derivative of tangent, if we rewrite tangent as sine over cosine, it's the derivative of the top times the bottom minus the top times the derivative of the bottom. The derivative of cosine is minus sine over the denominator squared. Notice we have a negative times a positive times a negative. That'll make that positive. Cosine times cosine is cosine squared. Sine times sine is sine squared. Cosine squared plus sine squared is just 1. So we have 1 over cosine squared. Well, 1 over cosine is secant. 1 over cosine squared would be secant squared. So the derivative of tangent is not just secant, but secant squared. Now we could use that same logic to get the rest of these, but I'll just give these to you. The derivative of secant is secant times tangent. The derivative of cosecant is negative cosecant times cotangent. And the derivative of cotangent is negative cosecant squared. So for tangent is secant squared, for cotangent is cosecant squared, negative. For secant, it's secant tangent. For cosecant, is cosecant cotangent, negative. So let's try to use some of these derivatives. So they ask us to find the slope of the tangent line at this point. So if we need the slope of our graph at a point, we need the derivative. So the top is 3 plus cosecant x. The derivative of the top is negative cosecant times cotangent. The bottom is v, so minus cosecant 7 minus cosecant, so v prime is 0 minus, and the derivative of cosecant is minus cosecant cotangent. Two negatives, that would make that a positive. So remember, the derivative of a quotient is u prime v minus u v prime over the denominator squared. So put in u prime put in v minus u times v prime all of that over the denominator to the second power. Now we could do some distributing. We could combine like terms if we have any, things like that. That would be all fine and dandy, but we're looking specifically for the slope at this point. So instead of distributing, combining like terms and so forth, let's just plug in pi over 6, or do we want to simplify? I don't guess it'll hurt to distribute. Let's do that for kicks. So if we distribute here, we're going to get a -7 cosecant cotangent. If we distribute here, negative times negative would be a positive. Cosecant times cotangent times cosecant, that would be cosecant squared cotangent, because we have two cosecants multiplied together. When we distribute here, we're going to have 3 times cosecant cotangent and then we're going to have cosecant squared times cotangent. This times those will be cosecant squared cotangent. This times those is 3 cosecant cotangent. And then there's a minus in front of that. So that's going to be -3 cosecant cotangent. And then minus cosecant squared cotangent. Now, we did not have to do that, but the reason I did is just because I recognize that those were going to cancel each other out, and that's going to make things slightly shorter. So our derivative, we have a -10 times cosecant x times cotangent x on top, and then 7 minus cosecant x to the second on bottom. So we want to find the slope specifically at pi over 6. So -10 times cosecant of pi over 6 times cotangent of pi over 6. Let's take the equal sign off there because we're now we're finding not just y prime, but our derivative at pi over 6. So we can plug pi over 6 in for x. So everywhere we have an x, put a pi over 6. And then we have to ask ourselves, well, what are these values? So if we think about a unit circle, pi over 6, that's 30 degrees. At 30 degrees, our ordered pair is √3/2, 1/2. Cosecant is the reciprocal of sine. So if sine is 1/2, then cosecant is 2/1 or 2. Now cotangent is y over x, so cotangent would be x over y. So √3/2 over 1/2 or times the reciprocal. So cotangent would be √3. So in place of cosecant, we're going to put 2. In place of cotangent, we're going to put square root of 3. On bottom, we have 7 minus. In place of cosecant, we have a 2, and that's squared. So that's -20 roots of 3 over 5 to the second, so 25 roots of 3. 5 goes into 20, 5 goes into 25, so -4 roots of 3 over 5. So that's the slope specifically at the point that they gave us. So we had to use the quotient rule to get the derivative, and then we had to substitute pi over 6 into our function. We did not necessarily have to distribute to cancel out. We could have substituted in here. Either way is fine. Here we're asked, where do we have a horizontal tangent line? So what do we know about horizontal lines? Their slope is 0. So we want to know, where does our function have a slope of 0? Well, where do we find out about the slope of the function? The derivative tells us the slope of our function. we have a quotient, so we need the derivative of the top, and we need the derivative of the bottom. So the derivative of the top, bring the 2 down, x with 1 less power. On bottom, the derivative of x is 1. The derivative of 7 by itself is 0. So our derivative, u prime v minus u v prime over the denominator squared. So u prime is 2x times v minus u times v prime over our denominator squared. So we get 2x times x, that's 2x to the second, minus 14x minus x squared times 1, so minus x squared over x minus 7 squared. 2x squared minus 1x squared is 1x squared minus 14x. Notice, even though this is not asked for, this function is not differentiable at 7. X can't be 7. Because if we plug a 7 into that derivative, it's undefined. Not differentiable at 7. So we want to find out, when is our slope equal to 0? What tells us the slope? The derivative. So when is our derivative? When is that equal to 0? Well, we could clear our fractions by multiplying both sides by x minus 7 squared. Those would cancel, and we would get 0 on the other side. But instead of having to show that every time, notice we have one fraction on the left. And if we have a fraction that equals 0, how do you have a fraction that's equal to 0? It's when the numerator is 0. So in order for a fraction to be 0, the top has to be 0. So once we have our derivative, set it equal to 0, the only way this can be true is if the numerator is 0. We want to factor the left. If we set each factor equal to 0, we would get x equals 0 and x equals 14. So those are the two x values where our slope is 0, where we have a horizontal tangent line. Now, it also says determine the point. Those are just the x's. So how do we get the y values? Well, we substitute them into our function. So if we substitute a 0 into our function, we get 0 squared on top over 0 minus 7. So 0 over negative 7, that's 0. If we substitute a 14 into our function, we get 14 squared on top over 14 minus 7. So 196 over 7. 196 divided by 7 is 28. So when x is 14, y is 28. So those are our 2 points where we have a slope of 0 or a horizontal tangent line. Now the next problem, notice it does not tell us what our functions are. At least not what g is and what h is. We're told how g and h are related to f, but we're not told a function of g. We don't know what g is, and we don't know what h is. So how are we going to find this? We want to know what is the derivative of f. Well, notice the relationship between f, g, and h. F is some function that is defined as a quotient of g on top, h on bottom. So if we think about our quotient rule, this is just how do we take the derivative when we have a quotient? Well, the derivative of a quotient, if we have something over something, assuming that this is not just a constant on bottom, is the derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. So the derivative of f is the derivative of the top, so u prime, or we could call that g prime, times v minus u, also known as g, times the derivative of the bottom, all of that over the bottom squared. So that's how the derivative of f is related to g and h. So if we want the slope, we would need to know g prime of 2, h of 2, g of 2, h prime of 2, and we would substitute those in. So notice we don't even know what the function g and h are, but since we know how they're related to f, we can use this knowledge to find f prime at 2. So g prime at 2 is negative 2. H at 2 is negative 1. G at 2 is 4. H prime is 4. And H is negative 1. That's going to get squared. So G prime H, G H prime H squared. So negative 2 times negative 2. 4 times 4. Negative 1 times negative 1. So we get negative 14 over 1, or negative 14. So it's just knowing the quotient rule here. All right, another concept that's covered in section 3 is higher order derivatives. If we have some function and we take the derivative of it, then we call that f prime. If we take the derivative of the derivative, we call that a second derivative, or f double prime. If we take a derivative of the second derivative, that's a third derivative. And usually once we get past a third derivative, then we'll use notation like this. So this means a fourth derivative, a fifth derivative, and so forth. How is that related to this problem? Remember that velocity is the derivative of position. Velocity tells us how position is changing. So if I know how fast I am changing position, that's velocity. Well, what is acceleration? Acceleration is how fast velocity is changing. If velocity is not changing, it's not accelerating. But if your speed is increasing, then you're accelerating. If your speed is getting slower, if you're slowing down, that's a deceleration. So if we want to know how velocity, so acceleration is just the derivative of the velocity function. In this case, we have a quotient that describes a velocity. So we need to use a quotient rule. So we need u prime. 110 is a coefficient, and the derivative of a variable to the first power is just 1. So that's 110. On bottom, 4 is a coefficient. The derivative of t is still 1. The derivative of a constant by itself is 0. So the derivative of the bottom is 4. So using our quotient rule is u prime times v minus u times v prime over the denominator squared. Now we could simplify that a little bit. If we distribute 110 times 4 times t is 440. Oops. 440 t. 110 times 14 is 1540. And then 110t times 4 is again 440t. So the 440t's cancel. So our acceleration function is given by 1540 over 4t plus 14 squared. So if we need to know the acceleration at 5 seconds, we substitute a 5 in. So 1540 over 4 times 5 plus 14 squared. So that's 20 plus 14, so 34 squared on bottom. And we can get that as an approximation, or get that as a decimal. So 1540 divided by 34 squared, 1.33. So if position is in, give us units here. They didn't give us units here. But if position were in feet, change in position would be in, for example, feet per second, and change in velocity would be in feet per second, or feet per second squared. So if this were feet, this would be 1.33 feet per second squared. Like I said, I don't think they give us units here. But the main idea here is that if we know position, the derivative of that tells us how position is changing. A change in position over time is velocity. If we take the derivative of velocity, that's a second derivative. The way velocity is changing, a change in velocity is known as acceleration. So the derivative of velocity gives us acceleration.